we briefly talked about continuity last class. We're going to continue with it today and do intermediate value theorem. Raise your hand if you've learned intermediate value theorem before. I figured most of you would probably have heard this. So we finally get to do something specific to calculus today. So I know continuity, again, you've dealt with in pre-calc. It's just a lot of the same stuff. But we'll just kind of talk through this. So we talked about how in Algebra 2 we define continuous, or we told you continuous, but if you trace with your test, you have to take it up. And last class we talked about the specific definition of continuity, and it has these three conditions. And you must meet all three conditions in order for the function to be continuous. And this is continuous at a specific point. So let's go ahead and specify them there. So this is definition of continuity. Whoa, that's... And you'll see it says at C. So what that is at an interior point. Meaning not an endpoint. Okay. Now, we are going to also go ahead and write down what it means to be continuous at an endpoint. So we're just going to sneak that information in here. You probably won't have to deal with that very much at all whatsoever. But we're going to go ahead and sneak that in there. So continuity at an endpoint is a little bit different. Same concept, kind of only one sentence. All right, so at an endpoint, let's first take a look at our left endpoint. Alright, so for our left endpoint, what we need to have is the limit as x approaches a from the right-hand side. We're saying that a is our left endpoint of our function. Okay, so the limit as x approaches that endpoint from the right-hand side of our function needs to equal the actual function value at a. So it has to equal f of a. So that's my left endpoint. For example, let's just say that our graph stopped here on the left-hand side. To be continuous at this left endpoint, we need to make sure that the limit as we approach it, and of course we have to approach it from the right side because it stops going to the left. We have to make sure that the limit as it approaches it is the exact same thing as that actual endpoint value. That's just to basically guarantee that the graph is continuing and meeting up with that point. So our right endpoint is that same concept, but just on the right side. So our right endpoint is going to be the limit as x approaches. We'll call our right endpoint b because it's a different point than a. And we're going to have to come from the left this time. Because again, if we think about this, let's say that this is my right endpoint, the limit as we come from the left-hand side, because there's nothing even happening on the right-hand side. So the limit as we come from the left of our function needs to equal the actual function value. So it needs to equal the actual value. Okay, so again, we probably won't encounter this a whole lot because most of our functions will be continuing on the ends. They won't be this, but if we were to encounter a function in which they asked about what is continuous, for example, square root curve, we can say that the square root curve is continuous from 0 to infinity. We can include that 0 value because we have the function value, the limit as it approaches it is the same. Does that make sense there? Questions on that? Alright, so we talked about how it can fail each of these three conditions, and we took a look at the different scenarios in which it might fail the conditions. This first one is where the function's not even defined, it failed that first condition. The second one here, my left and right hand limits are different, so it failed the second condition where the limit does not exist. And this third one, we have the function defined, we have the limit, but those two values are not the same. Okay, so these are kind of two different types of discontinuities you might see. Alright, so we'll just do a few of these, but it says determine if the function is continuous at the x value. Again, we're talking specifically at a value question. And if not, determine which of the three conditions it fails. So as we do these, we are going to go ahead and systematically go through condition 1, state what it is, whether or not it meets condition 2, and then when it finally fails a condition, that's where you can stop. So for letter A, our first condition is the function value itself. And what is f of 0? Undefined. Good. So remember, limits do not exist, function values are undefined. So f of 0 is undefined. So that has immediately disqualified us from being continuous at that point. So we can go ahead and say, therefore, f of x is not continuous at x equals 0, because again, we're talking about just this specific point. So therefore, f of x is not continuous at x equals 0. And then we're going to say this next part only because it's specifically asked for it. If not, determine which of the 3 conditions it fails. It failed number 1. Typically, though, we wouldn't outright state fails number 1 or fails number 2. But you would go through the steps, and then once you hit one that it does fail, you would say it's not continuous at that point. Now notice we can't just say f of x is not continuous, we are investigating a specific point. If you ever see the notation, you hear me say the function is continuous. Just plain old, for example, letter C, I can say this function f of x is continuous. That means it is continuous on its entire domain. So any values within its domain, it is continuous at it. But this part specifically, we're looking at these individuals. All right, so then letter B here. I'm going to go ahead. We'll just squeeze it down here. All right, so again, the first condition is f of 1. And what does f of 1 equal? -3. All right, so we haven't failed it yet. Or rather, it hasn't failed us. All right, now our second condition, we can see from the graph it does not exist, but I need you to break that down for me, show me where that fails. So we need to go ahead and state what the left-hand limit is and what the right-hand limit is and show that those are not equal. So let's start off with the left-hand limit. The limit as x approaches 1 from the left of f of x. What does that equal? -3. Now, to save myself a little bit of writing, I'm just going to go ahead and leave a gap here and then start writing my right-hand limit. Because if I listed them separately, I would then have to make another statement saying the left-hand limit does not equal the right-hand limit. And that's more writing that we really have to do. So we're going to be smart with the organization here and just put them side by side and put either a big old equals or a big old not equals. Okay, so saving you from having to write another step of formally stating it, we're going to find them and state it all in one. All right, so we have then our right-hand limit. So again, I'm going to leave that space. Now I'm going to do my right-hand limit. The limit as x approaches 1 from the right of f of x. What is my right-hand limit? 2. All right, do my left-hand and right-hand limits exist? I mean, are they equal? No, so now I'm going to slap in that big old does not equal. So there I've gone ahead and stated what they are and said that they were not equal all in one sentence. So because they are not equal, then that means my limit, my overall limit, x approaches 1, does not exist. All right, so again, we need to show where that breaks down. So overall, my limit does not exist. So is my function continuous? Nope. Therefore, f of x is not continuous. At the point in question, x. Is it a long and tedious process? Yes. So I want you to go through after doing these, do each step, and once it fails, then you can go ahead and make that statement that it is not continuous. But I do want to see each of these out. Because in order for it to be continuous, all 3 must be done. Now we talked about how that third condition is kind of encompassing the first 2. If my value equals the overall limit, then it kind of says that the first 2 are true, but this is kind of a therefore from the first. This is our continuity statement. The definition of continuity is that you have all 3 properties. So in order to say that a function is continuous at a point, you must show all 3 properties. All right. let's go and do E here. All right, first glance, algebra 2, is this continuous? Yes. Got a nice view, didn't have to pick up my pen. So let's go and just fly through statements. So f of 1, what does that equal? 2. Now here, since my limit does exist and we can easily see what that value is, I don't expect you to say left hand equals right hand equals overall equals. You can just go ahead and state that the overall limit is indeed 2. Up here, I wanted you to state the individual ones to show where it broke down, where it specifically failed. All right, and what was that third condition that we haven't gotten to yet? Okay, the first one's equal to the second one. Now you can't just say 1 equals 2. You got to actually state that f of 1 equals the limit as x approaches 1 of x. Therefore, f of x is continuous. And here our point of question is 1. So it's continuous at x equal 1. Okay, questions on that? So again, I want to see those 3 conditions. Unless it fails, then you can write how it fails and then say if it's not continuous. I want you guys to go ahead and try, let's go with I. No, not I. Let's do H. H looks better. There's an atom. Did we get it fails too? Okay, so left hand, right hand are not equal, so that means the overall limit is not equal. So therefore, f of x is not continuous. And this is when you realize just how long of a word continuous is. At x. Questions on that? Yes.
Why do you ask
you know, I agree with you. I'm not so sure that I trust this picture here because from everything I know that if you have an asymptote, you can't have a point defined there. Yeah, I find it fishy as well. I wonder, because obviously it's a piecewise, but can you have a piecewise? Can you still have the point on the asymptote? I don't know. I need to look into it. I feel like it's fishy. Yes?
Do we ever need to write fails like number 1 or number 2?
Oh, whoops. The instructions asked for it, didn't it? Okay, yes, here, yes, the instructions specifically ask for you to state which one it failed. If in general asks is it continuous at the point, if so, or if it's not, state why, then you can just state this here. When it specifically asks which one did it fail, then we'll say fails whichever. So this one it failed too. like on an AP exam, they're not going to say which condition did it fail, 1, 2, or 3, because it could be that in a different textbook, maybe they have these flip-flopped. So to justify continuity or to show where continuity fails, just show those steps and say why it is not continuous. Let's see. Oh, this one was continuous. It didn't fail. This one failed 2. Other questions with this? All right, let's move on to more exciting things. So I think we might have even talked last class, not last class, we've talked about it before, about our different types of discontinuities. We have those holes, which is when we have that factor reduce. When it says crosses out, that's not good mathematical language. Reduces from the numerator and denominator. So we know whatever factor that is that reduce out, then that's going to be where our hole is. We have jumps, and this really comes from piecewise functions. Or as we've also learned earlier, that our absolute value of x over itself is also going to give you that jump. But this, we said, is actually defined as a piecewise function, so it's just piecewise. And then we have our infinite discontinuities, which are vertical asymptotes. So this comes from our rational functions, and that's when our denominator cannot equal 0. Okay? So these are the words that you want to use. Now, in a more general sense, holes are removable. Jumps and infinite discontinuities are non-removable. So if you see that terminology, that's what it means, non-removable. So we have the removable discontinuity or non-removable, but jump and infinite discontinuities. All right. So that same as algebra 2, same as 3. Now our properties of continuity. This is something that's pretty important here because we have certain existence theorems in calculus, and part of them, the very first statement is, if a function is continuous, then blah, 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 blah. So in order to use those theorems, we have to determine whether or not the function is continuous. All right, so some properties of continuity. I want to first take a look at the right side here. First of all polynomials are continuous. If you think of x squared, x cubed, really any polynomial, there is no issue for x. There's nothing that x cannot be. The domain is not restricted, so it's continuous. Also, keep in mind that your absolute value graph, just your normal absolute value graph, is also continuous, right? If we think of that. So if you think of your parent functions, polynomials are continuous, absolute value is continuous. Can you guys think of any other of our parent functions that's continuous on the whole domain? Give you a hint. Well, quadratic is one, but it's part of our polynomial category. 5th letter of the alphabet. 5th letter of the alphabet?
Jeez.
Yes, our exponential graphs. So if we think of our exponential graphs, good thing there's more to calculus than just counting, right? Our exponential graphs, if you think of those are also continuous forever. Trace, sine, and cosine are continuous on all real numbers, but tangent has some issues. Cotangent has issues, cosecant has issues, cosecant has issues. Now, so these are what we say are continuous on the all real numbers. Now, as we talked about before, a function can be continuous just on its domain where it's defined. So, for example, even radical functions, if you think of that square root curve, it is continuous on its domain, meaning it's continuous from 0 to infinity. So polynomials, exponentials, sine and cosine, absolute values, those are continuous on their domain, but their domain is all real numbers, whereas my square root curve is continuous on its domain, it just has a more limited domain. Okay. So even radical functions are discontinuous when underneath it is negative. So it's going to be continuous for this being greater than or equal to positive. Sorry, greater than or equal to 0, meaning it is positive. Odd radical functions are continuous everywhere. So if you think of your cube root curve, that's continuous everywhere as well. So that's any odd root functions, or fifth root, seventh root, cube root. And then our rational functions is that other big kind of issue that we can have with continuity, where it is discontinuous when our denominator equals 0. So kind of in the world of math, our big mathematical blunders we can make is dividing by 0 and taking the square root of a negative. Now we know that the square root of a negative is imaginary numbers. There's an entire branch of mathematics called complex analysis, which deals with the imaginary numbers. Calculus, AB, is set in the real number system, so no imaginary, so we're not going to be dealing with that. So for us, our issues are dividing by 0 and taking the square root of a negative number. Okay. And then, of course, if there's a piecewise function, or that whole, or that asymptotes, that's where we're going to have some more of this calculus. All right, so then if we do have two functions are continuous at this specific point, x equal to c, then we actually have these properties also hold true, or these functions also hold true. So again, f and g are continuous at c. So again, looking at the specific point, then we can say that our scalar multiples, so if we take, let's say, 5 times the function f, that's still going to be continuous at c. If you think about it, the function x squared is continuous at 0. So thus the function 5x squared is going to be continuous at 0. Again, if f and g are both continuous at c, then I can actually add or subtract those, and whatever resulting function I have is also continuous at that point. If I take those functions and multiply them together, whatever resulting function I have is continuous at that point. If I divide those functions, as long as my denominator's value is not 0, because we can't divide by 0, I can divide those functions, and whatever resulting function I have is continuous as well. And interestingly, the composition also holds true. I can take f of g or g of f, and that function is going to still be continuous at that point. Okay? And you kind of dealt with this in pre-calc some, where they would ask you to find the points of discontinuity, or maybe they didn't ask you points of discontinuity, but they asked you for the domain of the function, and you'd have to consider places in which the domain did not exist. So divide by 0 or that square root of a negative number. All right. So this is helpful for us in trying to find points of discontinuity. For example, A is really made up of the scalar multiple of that guy, a scalar multiple of this guy, and we're adding and subtracting functions here. So we know that this one's continuous, we know that one's continuous, we know that one's continuous, so this whole function here is continuous. Or we can just go back to the fact that polynomials are continuous. But that's where it comes from. Okay, so this is going to be kind of back to that pre-calculus of find any points of discontinuity and determine which type. So we're kind of looking for those breaks or issues in the domain. Because we know that we'll have discontinuities with rational functions where that vertical asymptote is poles, if those appear, and our radical functions, it's only continuous on that domain that it's defined for. All right, so letter A. Do we have any points of discontinuity? Nope, it's a nice plain old polynomial, so we can just go and say f of x is continuous on its domain, which is just negative infinity equal to 2. All right, letter B, do we have issues? Yeah, we definitely have issues. What is going to be my problem here? X can't equal 2, it also can't equal something else, negative 2. So the issue is that we cannot have this equal 0. So x squared minus 4 cannot equal 0. So x squared cannot equal 4. So we get that x cannot equal negative 2 or positive 2. What types of discontinuities are those going to be? Infinite. Remember, wholes only comes from when we have a factor reduce. If it makes my denominator 0 and it doesn't get reduced out, then we have that asymptote. All right, so we have, what is the question? Find any points of discontinuity. Okay. So these are both infinite discontinuities, so infinite discontinuities. X equals -2. Could we have both an infinite and a whole at different points? Yeah, at different points, not at the same point though. Alright, alright, let's take a look at F. What's my restriction for F? We can't have this be negative, so in other words, we need 3x minus 5 to be greater than or equal to 0. We can have it be 0. We know this is 0. So then what does x have to be greater than or equal? 5/3. Add that 5 divided by 3. So we don't really have a discontinuity here. What we have is just that it's only continuous on a specific interval. So again, this is continuous on its domain, but its domain is going to be 5/3 and bigger. So f of x is continuous on the interval, and we can include that 5/3 to infinity. So we didn't have a hole, we didn't have an asymptote, we didn't have a jump, but it's not continuous on all real number system, just a part of that. So I didn't find much. All right. I want you to go ahead and try. Let's see which one's strong. Go ahead and do D and H. For D, how many discontinuities did we get? 2. What kind were they? What was one of my discontinuities? And where was removable located? Wait, we're just listing them. Okay, I'm sorry, I'm going into too much here. Alright, so we had a removable discontinuity at x equal to 3, you said? -3. Okay. And then what was my other one? Infinite, and where was my infinite located? So what did you have to do to find these? Yeah, we had a factor, and we ended up having our x plus 3's reduced. Do we agree with that? Okay. And what's our conclusion for H? It's continuous the whole time on its entire domain, which is all real numbers. Alright, questions on this? Okay, so now let's take a look at what happens with piecewise functions. Now, if they're piecewise functions, we know we have the potential to have that jump. There might even be that hole that's not filled in. Or it could be nice and smooth and continuous, but that's what we have to investigate. Okay, so remember, in order for it to be continuous, we have those three conditions. Now, it's asking if f is continuous, which means continuous on its whole domain. But we know, for example, letter A, that this top part, we know that that's continuous. It's a polynomial. We know that this bottom part is continuous. That's a polynomial. So our problem is not with the individual pieces, but rather with where they meet up. We need to determine, do these continuous functions meet up at the same point, thus connecting continuous with continuous? Or are they at separate points, which means you have continuous and then a break in working continuity? Okay. So to determine whether f is continuous, we've got to investigate this point in question. Okay, so let's first of all check our first condition. Is my function even defined? Is my function even defined at that point in question? Is it even defined at 2? And is it? Yeah, we have it has x is greater than or equal to 2. So when we plug it in, what do we get? 0. Yeah. Okay. Now, again, we know it's continuous everywhere except we're not sure about here. So we're investigating that point there. So we need to look to see, does my left-hand limit at that point in question, so as x approaches 2 from the left, and again, let's specify which function we're using, negative x plus 2. And we need to see, does that match up with the right hand? Alright, so when we test that first one, what do we get? 0. Okay, so let's go and leave that gap to decide whether it's equal or not equal. And let's test the right hand limit. The limit as x approaches 2 from the right. And again, specify which part you're using. When I take 2 and substitute in here, what do we get? Ooh, wonderful. Put a nice big old equals in there. So my left hand and right hand are equal, which means that those functions do match up at the same point. So let's go ahead and state that second condition, that the limit as x approaches to the overall limit of f of x. Awesome. Now that third condition is again, do the first and second match? And do that. Yeah, so f of 2 equals the limit as x approaches 2 of f of x. Therefore, can we conclude continuity? Yes, therefore f of x is continuous. And again, just making that statement is continuous, we're talking about is continuous on its domain, which is domain here, as we can see, is on it. Alright, questions on it? Now again, do be careful, you might have instances like letter F, the potential for a hole, maybe even just the potential for a jump there, we're not really sure. You can kind of see that with I as well, and H, where we have x does not equal single value, but then it's defined in a different way. Be careful, you could have that hole or that jump, so you got to check that point in question. And you'll notice too, like for here, -1 is what would be our asymptote there, although you can probably factor reduce. It might have been a hole there. So just make sure you're checking that point in question. Is it defined in the first place? Does the limit exist? And how big? Okay, now these bottom ones here is AP's. One of the favorite things to do is make you solve for that unknown value. So here it says find the value of the constant k that will make it continuous. So right now we don't even know what this function looks like because k is not defined. We want to find k that will make it be continuous. Alright, so in order for the function to be continuous, again we need for it to be defined. We see that it is defined. And we want for that left-hand limit and the right-hand limit at that point in question to be the same. So what we want is for this function, we want it to be equal. We're literally going to write that little word want. So I want my top, my first piece of the function, to equal the second piece of the function, specifically where? Good. So we want to specify at x equal 1. We don't want them to be equal the whole time, otherwise it's just the same function. We want them to be equal specifically at x equal 1. They can be different other places. Alright, so we want these to be equal at x equal to 1. Again, I don't know what k is, that's what I'm solving for. So what am I going to do with this x equal to 1? Substitute it. So I would have 5 times 1 plus 6, 2k minus 1. So we get 11 equals 2k minus 1. What do we end up getting for my k value? 6. Okay. Alright, so k equal to 6 is going to be the function, or sorry, the value that will make that piecewise function. Alright. Questions with that? Alright, let's talk about what's this? Your guys' next page is intermediate value theorem, right? Not this guy, right? Something else. Okay. All right, intermediate value theorem. Finally, something actually calculus. All right, so you can read this blurb on your own. Basically, what it says is that we have these existence theorems, and these are important to calculus because this, and important to rural problems because that lets us know if a solution exists. We might not know exactly what it is, but knowing that it exists is helpful. So our first existence theorem that we're going to be talking about is the intermediate value theorem. We'll also learn about the extreme value theorem and the mean value theorem and Rolle's theorem, which are all great. So the intermediate value theorem, notice the words intermediate value. Now you are allowed to use this notation. This is one of the few abbreviations allowed on the AVT exam, IVT. All right. If f is continuous on the closed interval a to b, so it's continuous between two endpoints, and our endpoints are not equal, and we have our y values associated with those endpoints, and there is some value in between those y values. Okay, so we have y value, some k in between there. Okay, so now between those. Then there is at least one number c in our x values such that that y value k matches up with the y value of c. Now this should be an open interval, so if you would fix that on your notes, that should say open interval AB. Okay. Alright. So the intermediate value theorem, you'll notice we have to have a few conditions met. First of all, f of x, or whatever the function is, needs to be continuous in order for us to even use the intermediate value theorem. Secondly, we need to have k be in between those y values. If those are both true, where the function's continuous, our endpoints are equal, and that k is in between our y values, then we know we can apply the intermediate value theorem and we have this result here. Okay. Now there is a special case of our intermediate value theorem, and this is specifically when a is less than 0, and a is greater than 0, b is less than 0. So we have a positive, we have a negative. If that's the case and it's continuous, it has to cross 0 somewhere. Okay, that's what this special case is saying. Let's go ahead and draw out what this is saying. I feel like it'll help you out visually in understanding what this theorem is saying. All right, so again, f is continuous, okay, on the closed interval a to b. So let's plop down an a and plop down an b. All right, and our endpoints cannot have the same y value. All right, so let's just go ahead and draw a continuous function. Something like this. All right, we've got a continuous function on the closed interval from a to b. All right, and my endpoints here are not the same height. Okay, so we've met those first conditions so far. So then this value here is going to be my f of a. That's my y value associated with it. And this value here would be the f. So we've got a continuous function. We can see our endpoints. We can see those y values. All right. So what we then have, it says, and k is any number between f of a and f of b. So plop your k down wherever you want it. Alright, so if we have this scenario, continuous, endpoints are not the same height, and there's a k in between my y values, then the intermediate value theorem tells us that there must be a C value in between, so in that interval, where that Y value, f of C, is that actual value K. So basically what it's saying is, if we have this smooth and continuous curve, then every X value in between A and B has a Y value somewhere between F of A and F. That's kind of the general version of it. So specifically for our special case here, let's change it up. Again, let's just throw A and B down. But it said F of A has to be positive, so let's keep our graph up there. But let's make F of B negative. Okay, so again, just draw some smooth curve there. You can twist it all around you want, as long as it's a function. So our special case then, as you can see, now if my F of A is positive and my F of B is negative, then at some point it has to cross 0. It has to have a Y value of 0. So that's what this is stating here. At some point, that C value F of C is going to be 0. Okay. So one's positive, one's negative. It has to cross the x-axis somewhere. Now, if they're both positive or both negative, then we just have that basically every Y value in between here is going to have an X value associated. Now, you might have more than one. For example, if this graph would have come back up around, you'd have that Y value twice. Right. So real world examples of this, let's talk about height. If you're 4 feet 2 inches tall on your 10th birthday, but then by the next year on your 11th birthday, you've grown to 4 feet 7 inches, there has to have been a time between 10 and 11 years old when your height was exactly 4 feet 4 inches. So my height falls in between the beginning and ending height, which means at some point in time between my x equal to 10 and x equal to 11, sometime within there, my height was exactly 4 feet 4. We know this because human growth is continuous. You're not suddenly 4 feet 2 one day, and then in an instant, you go 4 feet 7, right? We actually grow slowly over time. Same idea with throwing a ball. So if I throw a ball from the ground and it goes up to a height of 20, then at some point in time, it has to be at a height of 19. So from 0 seconds to however long it takes to get to 20 feet high, at some point in time within that time interval, it has to be 19. Okay, so this, we're not always going to solve for the value at which this occurs, but we can determine whether or not that value exists. All right, let's go and flip this through. So for example 1, and this is a typical type of AP question of the way that they might ask you something about the average. They're not going to tell you to use intermediate value theorem. They need to know that you remember it and understand when you can apply it. Remember, for IVT, it needs to be continuous, and our endpoints need to not be the same. And so if we can determine a certain Y values in between the Y values we have, then we know that there is an X value that is associated. All right, so the car travels on a straight track during the time interval 0 to 60 seconds. The car's velocity measured in feet per second is a continuous function. The table above shows selected values of this function. It is helpful that they told us it's continuous because we don't have a function to determine if it was continuous otherwise. So A, for time 0 to 60, must there be a time when your velocity is -3? Justify your answer. And again, this is typical fashion for AP. They love those words, justify your answer. All right, so we have 0 to 60. So we're going here to here. And they asked, is there a time when V of t equals -3? Well, let's think about it. Does -3 fall in between -20 and 10? Yeah, in fact, we could probably slap it somewhere, be somewhere within here, right? So my Y values go from -20 to +10, which means it must have at some point crossed -3. So they're asking us, did that occur at a specific time? And we can say, yeah, it had to have crossed at some specific time. We could probably even narrow down the window here. So we have, again, first, is my function continuous? Yes, they told us that. So we need to state V of t is continuous. has to be met in order for us to use IVT. Next is the value that we're considering in between the y values of the endpoints. Yes. So it's usually good to go ahead and state those endpoints. So v of 0 equals -20, and we had v of 60 equals 10. Okay, so state those, and then you can just go ahead and say v of 0 is less than -3, which is less than our v of 60. So y value endpoints surround that point in question. Okay, so that was kind of our next thing. I guess I probably should have put 2. Alright, so the condition of continuity has been met. The condition that the y value falls between your y values and your endpoints has been met. So thus, we can use intermediate value theorem. Alright, so now we can make our conclusion. Thus, by IVT, finally something we don't have to write out, there is a C value. And where does our C value have to occur between 0 and 60? So there's a C value so that 0 is less than C, less than 60. Alright, so there's a C value so that 0 is in between, sorry, C is in between 0 and 60. And we can say that V of that C value is the point in question. Okay, so this will be kind of the format that we follow each time. First, state whether or not it's continuous. Go ahead and state what those endpoints are. It just shows that they're not equal. And then we state that the y value is in between. Then we can claim it. Okay, your homework is in 4. I'm going to pass it back. And you're going to stinger 7 and 8 today. Hopefully you like 7 and 8.